All right, Nick, if you could check to make sure that we're streaming and get in my ear if it's not going, okay? All right, how are we doing today? That good? That good, huh? Awesome. Glad to hear it. All right. So, a couple orders of business. So, hopefully, you all are getting cracking on homework number one. Um, and we're going to have a running FAQ page for people who have questions. A few people come to office hours already just for general guidance on the homework. We're happy to fill in more guidance if you need it. But in essence, what you're doing is you are taking the the regressions we were doing 2 weeks ago, where we are doing gradient descent to find all the coefficients of those models, and you're going to use gradient descent on models with more and more polynomials to them, right? You're gonna, instead of just being y equals mx plus b, a power one polynomial, you're going to do a quadratic in addition, and a cubic, and a quartic, and a quintic, up to a sixth order polynomial, and show how the fit gets better, but how the generalization error does it get better? Does it keep getting better? That's what you're going to find out, right? So you're going to have to take what you've learned from class and extrapolate it to a more complicated model with more decision variables, with more parameters that you're trying to fit. That's what we're trying to do today. So with that, so we're going to get started today. So what we started learning in class was how to do backpropagation. Backpropagation, I think, is a lot of fun. Because but what is the purpose of backpropagation? What does backpropagation get us? Why are we doing it on a neural network? What does it tell us at the end of the day? Anybody want to tell me what it gets us? A gradient. That's exactly right. It gets the gradient out. Excuse me. So it's the gradient, because these neural networks are complicated. Taking the derivative of them by hand certainly be very complicated, but even the computer algebra system can be very complicated. So it's a very algorithmic way of doing that. So we're going to start building some backpropagation from scratch on a whole new on a whole new Python notebook. We're starting fresh each time. I think that's a fine way to do it. We're not building too much on top of each other. We can start from scratch. Yeah, you can feel fresh every time, you know. So let's go to the board. I'm actually going to bring up our notes from last time. Okay. So what's going on with, oh, you know what? I should plug in. Excuse me, friends. Got to plug in my iPad. There's your problem. It's not plugged in. Let's see if that works here. Let's see if we can get this working. 1 second. I might have to fix. Oh, wait, there we are. Fantastic. We're so close. Awesome. So here we go. These are our notes from last time on backpropagation. And where these come from, so we had a forward propagation algorithm, okay, and a backpropagation algorithm. Now, my friends, you'd be forgiven if you looked at that and you're not a math aficionado and started panicking, okay? We're going to break down how to do these steps, at least in a simple case today. Okay, do a very simple forward propagation and a back propagation. The forward propagation evaluates the neural network. It tells us what the value is. You put in an input, what's the output? The output, then when back propagation takes the output, back propagates it, and gets the gradient. Okay, all right, the value and then the gradient. Yeah, so now we're gonna, so let's break down our task today. So what we're going to do is going to make a very simple neural network. We'll go back to maybe this, well, we'll just continue the same document and we'll just upload the whole thing when we're done. Okay. So coding, we're going to be coding backpropagation. I can't see your comments. Give me a second. I can't see your chats. Okay. So for those asking, yes, we should, for attendance, it's important to be on, at the very least, if you could put your name in the chat right now, so that way you can take attendance if you're on YouTube. If you prefer it on YouTube, I get it, but we do need to see. I mean, we can't take your attendance if you're not on Zoom somehow. So at the very least, put your name in the chat if you're going to log off for YouTube. And please don't just log off Zoom and then don't watch the YouTube. I really just there's the reason we do attendance here, friends, is it's to keep you up to date on the material, right? It's very easy. Like we're putting, look, this is all going out to the world for everyone, right? And you can be like, oh, I'll watch it at any time. We don't want you falling behind, because if you fall behind, the material builds on top of itself, and that gets you into a rough spot. We don't want that. So, all right. But I understand watching it on YouTube. Although I think that we've corrected, my friends, the what is it? The Zoom resolution issue. But on YouTube you can rewind. So I understand. Wonders of technology. Yeah, wonderful. Coding backpropagation and forward propagation. We actually did forward propagation last lecture in our own way. We kind of just fudged through it, right? We figured it out. But in the Goodfellow text, they have a nice formula for it, right? So awesome. So cool. Moving on. So let's start reasonably simple. So in terms of a neural network, we could do a fully connected MLP where we have many units, on each layer. But we're going to start with something very simple. Okay. So let's do a simple neural network where the interconnectivity is not the problem. Okay, there's not the challenge. It's so we're going to do just one. We're going to have one unit per layer. Okay, so let's say we have our input X. Okay, going to go into some activation function. We'll call it F. I believe we're calling it F here. 1 second. Yes, F. Activation function F, which goes into some other activation function F, and then comes out as some output Y. And that's the simple neural network. And again, this will just be a single scalar value. In this case, this X will just be a scalar. Just to keep it simple. The point is we now have multiple layers. You go into this activation, that activation comes out to Y. And then we need to evaluate the loss function. And so the loss function, I believe someone needs to mute. Nick, let me make you a... Excuse me? I can't mute here. There we go. Let me make you a co-host so we don't have to worry about that. Apologies. Okay, well, so while I'm doing this little bit of technical bits here, we're going to do that single layer neural network. And at the end, we're going to have some loss function that we're going to want to optimize. We're going to have a loss of a mean squared error, MSE. Okay? All right. All right. And the idea is, so what we're going to have to do is we're going to create this simple neural network. And our goal is going to be, we're going to do a forward propagation step and a backward propagation step. We're going to code forward propagation, then backward propagation, backprop, and then with that gradient that comes out, we can do gradient descent on the loss. Okay, so we can get it to fit some data. All right, now these activation functions, we're going to try to do a pretty typical activation function. We're going to do like we did last time. We're going to do the hyperbolic tangent, tan H, TAN hyperbolic of X. Okay. So those are the 3 things we want to do. See how far we get. Now, the thing we don't have to deal with is we don't have to deal with this going off into other nodes and then doing all these crisscrossing connections. Not doing that right now. Okay. So forward propagation. So now, according to our lecture notes, okay, we have a very specific algorithm here for forward propagation. All right. We have to, and let's go back a little bit further so we can get an idea of what we need to define. This is in chapter 6 of Goodfellow, right there. Okay. So we need to know what the network depth is. Okay. We need to know, we need to define some weighting matrices. These will actually be very simple matrices. They're going to be 1-by-1 matrices. And the bias term. We're going to need to define the vector of inputs. It's simple. Right now, x is actually going to be a scalar, just a single value, okay, as is the target output y, okay? And we're going to define the loss function. That's going to be the mean squared error, okay? So, and the way that we defined it, this is not, so for those asking, this is not for this homework, okay? This will be for a future homework, okay? You have all the tools that you need to do for your current homework from previous lectures. So just as a reminder, so when you have your x, it's an input into these functions here. Then whatever comes out of that activation function, we call h for a given layer. Then it gets multiplied by some weight w, the amount of which this, like that connection right there, that's how heavy that connection is. That's a weight. That's a number that we decide that we're going to learn via gradient descent. And the result of that multiplication goes into another neuron. In this case, it was another neuron, another neuron. Okay. So here we had 3 layers. Okay. In our example, we're going to have 2 layers. That's 2 layers, right? So we have 2 layers. Okay. Our activation function is going to be a tan h. So we can follow through with that algorithm in a somewhat simplified way in Python code. So let's see if we can get started here. And so our loss, by the way, it's a mean squared error, but with respect to what? Like, what are we trying to get this function to look like, right? And that depends upon data, right? So we are going to want to see if we can get it to give it, so we have to invent some data that we want this neural network to fit. Now, the good news is that it's a single input and a single output, so we can plot the input on one axis, output on another axis. Should be a nice, simple plot. So we'll figure out what we want it to, what we want it to actually approximate pretty shortly. Okay. So with that, let's actually go to Python here. I've just opened up a new notebook in Google Colab, colab.research.google.com. Okay, and I'm going to create a new notebook, and we'll call it Backprop. Okay. All right. I'm going to create a text block. This is going to be our first attempt at backpropagation. Make it a little bigger. All right, by Christian Hubicki and friends. Today on the 2026-02-05 of the Common Era. Okay. All right. So with that, we're going to want to create some. So the code that we're going to want to make is going to require some. Requires some importing. We need NumPy. So we have to start with importing NumPy. Import NumPy as NP. And we're going to start plotting with using matplotlib .pyplot as NP. Then we're going to import our relevant packages. And that's what we should really just need. Okay. Question. Okay. So let's create, should we create a function that we want to fit? Here's what we're going to, so question. That's just a mistake. It's PLT. Sorry, got distracted. Thank you very much for being on top of it. We would have learned eventually. We would have gotten that. Thank you. It's PLT. So I appreciate everyone's patience as I'm going through this. I'm paying attention to text comments and everything. So you're all being great. Thank you. So, all right. So we've got a, so what do we want to do? So let's define the function we want to fit. You know, we're going to be doing, this is going to be a supervised learning. This will be supervised learning, meaning that we're going to put in labeled data, a set of X and Y coordinates, and we're going to want to fit with a curve, right? So let's, you know, so we're going to have a curve that might look like, that looks like this, you know, and we want our neural network curve, the curve generated by this model, okay, which is a neural network, to be just like it, right? Okay. And we will try to get there by sampling data from this curve and say, hey, this is the data we want to fit, and use gradient descent to fit it. Okay. If you're at all confused about where this all fits together with everything else from the course, when we did the fits using the y equals mx plus b with gradient descent, this is exactly the same thing, except instead of y equals mx plus b, we have this neural network, and instead of computing the gradient just by hand, we compute the gradient with backpropagation. It's the same thing. It's just a more complicated model. All right. Okay. So let's define a curve for supervised learning here. So, and I'll tell you, if we are doing this for the first time, if you are building any piece of code for the first time, you want to try to set up a problem that you know that you have a real good answer to, that you know it should work, right? So when we're coming up with a curve for our model to fit, right? And we want to be sure that our algorithm is working right, let's pick something we know it can fit really well. I'll tell you what I mean. So imagine though, imagine we had a single neuron, okay, that looked like that went in like that, okay, and that was our only neural network, and we had weights for that connection and weights on the output, right? Something like that. Excuse me. And that neuron had some activation function. I keep drawing it over and over again. I'm sorry. And it had some activation in some neuron, right? What's a function that we know it can fit perfectly? Well, the activation function of this neuron, right? Like we know it can. So let's try picking a curve that we know for sure that with the right weights, it'll get it perfect, right? And if it doesn't work, we know we screwed something up. Doesn't that make sense? So that's a good way of debugging. So if our neural network is a tan H of a tan H, why don't we make our curve that we're trying to fit a tan H of a tan H, okay? And multiplied by a certain value and added to some bias, and we'll see if it gets us the right values, okay? So we know that in principle, so let's define a new function, okay? So we're going to define a function. We're going to call it target function. Something that we know we're going to use to generate our data with inputs and outputs, but our model is going to have to fit perfectly. And it takes in our input X, okay? So we define some function input X, all right? And it's going to return, whenever you put in X, it's going to return some, let's just say the hyperbolic tangent, which we get by, say, np.tan h of X, right? If we return the hyperbolic tangent, and then let's make a new code block where we plot. So plot the target function, okay? And we will do that by creating a bunch of X values. Oh, the problem, if we're using X in multiple contexts, it's okay. It's all right. We'll be fine. It's all within scope. So we're going to say an X list, a list of X values for plotting. Okay, or you know what? X plot. That's what we'll do. All right. And so we're going to take a whole bunch of X values we want to plot so we can plot our curve and a bunch of Y values associated with it. So we'll say np.linspace. What's plot from like -2 to 2 with 1,000 points in the middle. Okay. And then Y plot is going to be our target function equals, our target underscore function of X plot. And then we want to plot it. So we say plt.plot X plot and Y plot. And let's make it a black line for now. Okay. And so we want to plt.show to actually show the plot, open, close. Oh, you know what? I didn't run all, just hit run all, friends. And there we go. There we have our curve. Okay. Make that smaller. Yeah, we'll deal with that later. Okay. So that's our hyperbolic tangent, a single hyperbolic tangent, right? But our two-layer neural network is a hyperbolic tangent within a hyperbolic tangent. Okay, the result of that is going to be two hyperbolic tangents, one enclosed within the other. Okay, so let's make a function that we absolutely know will fit. So let's go here. Let's change the target function. So we say np.tanh of np.tanh of x, right? Okay. And we run it. Oh, I have to run all. We change the target function. Okay. Believe that did it. np.tanh, np.tanh. Yeah. It just kind of shrunk it a bit. Kind of shrunk everything. It's hard to kind of tell. Let's change the axis limits. So I think we say ax.plt.gca open close. Is that right? And we say ax.x.ylim. What do we say? -1 to 1. I'm just remembering the syntax off the top of my head. Y-ax limit. Let me check my old code. I'm blanking on this here. Give me a second. Yeah, Nick, if you could just give me the command for the axis limit. I just blanking on it at the moment. Still getting used to my Python syntax here. I'll pull it up in the meanwhile. So we're just going to change the axis limit. But in the meantime, do people understand any questions about, we're just trying to create a function that we know we can fit perfectly? Ax.setYlim. Thank you. Yeah, try that here. Sorry, right? Boom, boom. There we go. Ax.setYlim. There we go. Thank you, Jack. Appreciate you being on the ball. One day I'll be much more fluent in Python. We'll bang it out like that. Here we go. So there we go. We're setting the Y limits. We could set the X limits, but the X limits are fine. Okay. Ax.setY limit. Let's comment our code. Let's say this is just plot. Okay. Plot our curve. All right. So it can definitely fit that. Now, friends, I have a question for you. So please think, and I hope someone will be ready to respond. What would be the weights and biases of our neural network shown here? Oops, sorry, shown here that would achieve that exact curve? First one, how many weights are there in our neural network? Yeah, 2. I think arguably you can maybe put a third in the output, but yes, yeah, 2. Yeah. maybe a third one there off the top of my head. We'll get to that. But yeah, it's like 2 or 3, right? But regardless of what it is, what are the values of those weights that will achieve this response? Anybody? They would all be just the number 1. Exactly, right? So we know the answer. Is the answer. What about our biases? What would be our biases of each of these neural networks that kind of feed into those things right there? What's the offset of those that we add, the B's? 0. 0. Oh my gosh, how complicated is this class? 0, right? We're not adding any extra terms. Now, what I could do is I could add in here plus 3, which would mean one of our biases is 3. And I can multiply it by a weight. I could say it's 2 there, right? And I could do the same thing times the input here. I could say this is minus 1 times x minus 4. I'm curious how this works out. It might shift it past the axes. Let's see here. Let's see. Let's run everything. Okay. All right. I think that we moved it off the boil right here. Let's see. Let's change the limits here to maybe minus 5 and 5. Do you see people see what I'm doing? I am manually changing this target function so that we know that the optimal, there we go. There we go. Plus 3. Let's get rid of the y limits here. I'll comment it out so you can get the proper y limits. Oh, there we go. Right there. There's a new curve. I just got rid of the y limits. Let me just change it to the 0 y limit is 0. So I get a nice plot here. It's too much. I'm playing around here. There's our target function. 0 to 2. Let me show you the code so you can copy it down. I apologize here. All right. So we know that the answer to this neural network is going to have a weight of like minus 1, a weight of 2, and a bias of minus 4, and another bias of 3. Right? That's the right answer. So if we get all this code working perfectly, then we're all good. If we don't get that answer, there's something wrong, right? Once we have done our forward propagation and our back propagation and our gradient descent, okay, we don't get it right, we've done something wrong. Okay. With that, let's move forward to the next step. So now let's actually build our neural network and do some forward propagation. Okay. So let's do some forward propagation of a 2-layer neural network with only 1 neuron per layer. That's what we have up here, right? Right there. Okay. Okay. So according to our forward propagation algorithm, let's go back to what do we need to start with? We have our network depth. Okay, our network depth right there. L. So let's call that. So let's assign and initialize our variables. Okay, we have our, I don't like using lowercase l, it looks like a number 1. So let's just call it network depth. Okay, network depth, I'm going to say 2. All right. We're also going to need weighting matrices. Okay, and whoever said there were 2 weights is exactly right, because here are our weighting matrices. Now, our weighting matrices are going to be really easy. They're going to be 1 by 1. That's because our network is just, each layer has only like a 1 input that goes into 1 neuron. Okay, so 1 input into 1 neuron, 1 by 1. So we're going to create 2. We're going to create a list with 2 weights in it, okay? Particularly, we're going to create something called a tuple, okay? So let's see here. We're going to say that our weighting matrices, okay? We're going to try it this way, see how it goes. And we're just going to initialize it. So it's just the number 1, comma, the number 1. And yes, I'm putting it in parentheses. I'm going to try something here, all right? So the way that this works, okay, is that it's another kind of list, all right? But it's not like a NumPy array. So it's like a tuple. And what this allows you to do is to store not just numbers in here, but all kinds of different data structures. So if instead of I wanted a list of numbers like 1 and 2, I could have a list of matrices. And recall, as we said last time, there's going to be a weighting matrix for every layer, right? So wouldn't it be nice to have a list of all of our matrices so we can say, I want this one, then that one, then that one, then that one. And as a result, we could have this automatic list of weighting matrices that as this network gets bigger, we can just say, hey, I want more layers. I want more hidden unit. I want more neurons. And it automatically is able to loop through all those weighting matrices. When we covered this last week in code, we did not do this. We did it by hand. We said this layer, we'll do that. Then we'll copy and paste to the next layer. But since we are looping forward and we want to loop backward, let's try putting it in a list. All right. Does this work like a cell array in MATLAB? Yes. This works a lot like a cell array in MATLAB. Okay, assuming I'm not screwing something up. And today, who knows? Let's see. All right, so let's create a weighting matrices. Let's just show you how it works. We could print weighting matrices. This is way too much. We're going to say, we'll call it W list. Excuse me. Way shorter. Sorry. That's going to kill my fingers. W list. So you can print it. Hey, look, W list, right? And if you want to just get one element, we do the same thing where we say, hey, what's the 0th element of W list? It's 1, right? But the key difference is that if we want to have matrices in here, let's just create matrices filled with 1s, for instance, okay? Let's say NP dot 1s, which creates a list of 1s, a matrix of 1s, open close parenthesis, let's make it a 4x4 matrix of 1s. And let's make this a different one with a different size. Let's make this NP filled with 0s. And let's make it with a 3x3 of 0s, okay? Now if we rerun it, hey, look, the first element is this matrix, and the second element, which is, again, indexing starts at 0 is first, 1 is second in Python. There, right? And if I get rid of the indexing, look at that. Boom. You have both of them in the list. Pretty neat, right? Pretty neat. So, great, awesome. But let's go back to our initial values. Instead of doing matrices, let's just do 1 and 1 as our initial guess. Okay. Zoom in some. Is it blurry or is it just monitor stuff? Okay. I'm curious. Right? 1 and 1. All right, we got that. So we got, so we have our, we're initializing our matrices, and we want to do the same thing with the biases. Biases here. So every neuron's going to have a bias input. Okay. Okay. So we're going to have that. So we got a bias, which will be, so we'll call it the B list. And let's comment this here, but we'll say it's right now our bias is 0 and 0. This is these are our weighting matrices and our bias list. Our bias, sorry, our bias list, okay? Or I say list of weighting matrices and a list of biases, bias vectors. Cool. We got that. Keeping in mind, just for everyone's memory, okay, that you have some input X, it's multiplied by W, and you add B. So number of this W is going to be a matrix times X plus B W times X becomes a vector, and you add the vector to it. So, all right. So next we have that. X is a vector of inputs. We'll just call that X is our, so we'll set our input just to be 0 for now, or should we, let's just make it 0 for now, just to see if everything works. Okay, this is our input, right? At some point, we're going to want to try lots of different inputs for X. Theoretically, it'd be great to throw in a vector, but I'm not super confident on how us throwing it in a vector when we start doing a whole bunch of matrix multiplications, how that's all going to work. There is a way to make it work, but for our purposes today, we're just going to try just a number, and we'll loop that input in order to make a plot. Okay, so we got 0, and then our target output is Y. We will compute what that is. Okay, we also need to make a loss function. So we should also define a loss. Let's make another piece of code. Let's define so we need to define our loss function. Okay. So our loss function for any given data point, okay, is our mean squared error. And let's go back to our code here. And so our loss, let's write it down at the bottom here for our new thing. Our MSE loss, keeping in mind the MSE, so our L of all of our different decision variables, okay, is going to be our prediction Y minus our actual data point Y squared for every data point that we have. So when we actually, so we need to actually sum them up across many data points. So sum across I through n data points for all of our data points and the prediction of all our data points. Okay. And then we will divide by n. Excuse me. Apologies for the nonlinear math here. One over n, right? That's MSE. Okay, and that will give you your cost J, right? So what we need to do is create a loss function in our code. So let's go back to the thing. Let's do our loss. So let's define our loss. And let's make LOSS capital. We'll start creating a naming convention. Capital letter at the beginning is going to be a function. So loss function. Okay. In fact, let's start enforcing a naming convention. It's nice to have functions have different naming conventions than variables. Variables tend to be all lowercase, right? There are lots of naming conventions out there. I'm going to go back up to my function up here, my target function. Where is it defined? I'm going to say capital T for target function. I'm going to change this to capital T for target function, okay, to start to enforce some kind of naming convention here. I'm going to run all of them. Okay. All right, now we're going to define our loss function, and our loss function should take in every decision variable that we have. Now, all of our decisions for optimization are going to be dependent on what are they? They are all of our weights and all of our biases. Okay, so it's going to be all of our weights. So it should take in some kind of list of weights, which will be our weight list. We will send it in. We'll call it, I guess we can also call it W list, even though it'll be, yes, we'll call it W list here. Our B list, our list of biases. And we want to have an X data list, a list of X data points. All right. And Y data points. Okay. Semicolon, so colon. All right. So we've got our mean squared error should be a sum. It should be a looped sum here across all of this. So we're going to do a for loop. Okay. So we're going to have to do a for loop where we're going to sum up our loss J. We're going to say it's equal to 0. So we're going to initialize our loss at 0. But every iteration of the loop, we add to that 0, right? Every data point, we add this term on top. Okay, so that means we go for loop for some I is in range from 0 through the length of all of our data in the X data list. Okay. Okay. Basically, this is a loop that's going to say, hey, whatever size data list you put in, we're going to loop through every one of those data points, colon. And for every one of those data points, we're going to say that J is going to be equal to our previous J, and we're going to add on this term, which is your Y, okay, which is your prediction, and your yi. So that's your data point. That's the Y data point right there. That's the data point. Make it a little bigger. This is your data. It's prediction. The hat is the prediction. This is your data. Okay. That's going to be our loss function. So we're going to say, hey, that means we're going to need some prediction. So we're probably going to have to call the other function, right? So we're going to say we're going to create a prediction function. And you know, another function called, we'll call it predict. And the way it'll work is we will compare. It'll probably have to take in our list of weights and our list of biases, and all this prediction function is going to evaluate our neural network, or later on, when we're computing our derivative, it's just going to be, we're going to replace that with just the math here. Okay. All right. So for the derivative of the math, I'm sorry. All right. So actually, excuse me a second. For our loss function, we just send in our prediction, because our prediction comes out of our neural network right here. So we just need another. We actually got to change this up. We're going to say, we're going to send in our prediction. Y predict. That's what we're going to do. And our prediction and our cost function is literally this thing we're looking at. I'm sorry for overcomplicated. Right here. Right there, there's our cost function. That minus that squared. So it's going to be Y predict minus Y data list. Do we even need the data list? Give me a second here. All right. So Y data list, the current data point. We'll work this out here. Okay. And we got to square it. And the squaring in Python is that little 2, the little double asterisk, and then 2. Yep. So, all right, so that will add to it, but we send in a single prediction, would be a prediction for all of our data points. We'll figure it out. So I'll tell you what we can do is we can literally, what we will do is we will get rid of, we'll just say Y predict versus minus Y data. We're going to get rid of this X data. I don't think we're going to need it. Get rid of the list. And then get rid of the list. We only need the Y data point. I think that'll do it. That's all we have in this cost function, right? There's no X going in. There we go. We got it. Okay, and at the end, we got to get rid of this indentation. We return J. And right now, it's going to be very simple. We don't even need the loop for this one. So we'll deal with that later. Okay, this might be a little superfluous for the time being. Let's just define that loss function. Okay, we have the loss function. So let's now go back and build the neural network. Let's do the forward propagation. So the forward propagation, right up here, we have to start with some H0. Okay, so we're going to have these H's that are going to be these vectors that we're just going to store in the forward propagation. Remember this when we go back to the board, that when we go forward, we say that, hey, this is H0. And after it goes through the weight, after it goes through the function and the weight, it becomes h1. All right, which is another vector of all the outputs here. Then they go into this other layer, and this one becomes h2, and so on and so forth. So we have to store those. Okay. Excuse me. So we need to make another list of vectors. Let's go back to here. So let's make another list of vectors. So for our forward propagation, we need a list. We need a list of h vectors beginning at h0 and then up through HL. Okay, for the number of layers that we've got. Okay. Right now we have 2 layers, so what we will do is we will make an H list, which has, and again, this is like a cell array, meaning that it's an array where you have lots of different types of data types in it. So what we can is it's tuple. It's a little tuple, we call it. We're going to initialize. Okay, this being 0, 0, 0, because we need H0 and H1 and an H2, right? So we need 3 of them. Okay. All right, and just making sure, let's try saying, so we want to say the first element, we say H list 0 is equal to some input X. Make sure that works. Object item assignment. We can't do item assignment. We can't reassign. Hey, Nick, so we're going to do this a little bit easier. We're going to say H list 0 for now, okay? Create something, okay. So I made a boo-boo, okay? 2 tuples you can't change. Tuples you can't change after the fact. Once you make them, they're immutable. So we're going to say H list 0 equals X, and we're going to create things called like H0, H1, and H2, and afterwards we will fix it up into a loop. Okay. Yeah. Where's the 1 over n come into ln in the code? Well, right now we only have 1 data point, so we don't have to worry about it. Okay. Do I need y for yi for y predict? We've gotten rid of the i's, so we're all good there, right? Mm-hmm. Yeah, we don't. So, yeah, we need y predict I. So we do need a y predict I there. Okay. All right. So we're gonna do h list 1. Sorry. Okay. So h list 0 is going to equal x. And what we need to do is some kind of for loop. But right now our for loop is not going to work. It's not going to index through a list. So what we need is some kind of activation. Call this AK. So starting at 1 through L, we create AK is equal to BK, which we have to update later. And that. Okay. So just give me a second here. All right. So we're going to say that call it A1 is going to need to equal to B list 1. Okay. Sorry, B list 0. We just sorry, I'm not doing a good job explaining this. So this right here, this step here, we're setting our initial H0 to be this. See that? That's that step. Okay. Now we were trying to do a loop, but right now we're not looping. So we're just going to say that A1 here is equal to our bias list in the first element, which is going to be B list 0, okay, plus W list 0, that's this right here, times HK minus 1. Since K is currently 1, we need H0, which we are currently called H list 0. Okay, this is the forward propagation step, right? That's that step. Now, HK, which is going to be we'll call it H list 1, is equal to f of A of K. Well, f is our activation function. So we should define that as a function. Let's define that. Let's go up ahead and let's make a function up higher. Let's define an activation function. Okay. So the way we're coding is we're coding through and we're realizing, oh, we need a function. Let's make a function. So let's define, call it activation. And it takes in some variable x, colon. Okay. And our activation function we've already decided, we know, is tan h. So we're going to say that we're actually just going to return np.tan h of x. That's it. There's your activation function. Very simple. So we can so this h list 1 is equal to the activation. That's the activation of A of K, which is A1 currently. So we would say activation of A1, right? That's for list 1. Now we have to go on, loop back around, whoop, and now it's equal to 2. Okay, so we would say A2 is equal to, that's right here. So K is equal to 2, which is going to be our last loop, is equal to our bias, our B list, and our second element, which is 1, because counting starts at 0 when you index, plus W list 1 times H list 1. Okay. Then we need to define our H list 2. That's this step right here. Is equal to the activation of A2. Ta-da. Okay. Then our Y hat, which is our prediction, is equal to the activation of, well, actually, no, we're sorry, we've done the activation. I jumped to it. It's just equal to HL. What's HL? Well, L is equal to 2. That is our number, our last layer. So there we go. We've just got H list 2. Okay. All right. Now, our next step, we need to apply our cost function right there. Okay. J is equal to our loss function. Our loss function, how do we define our loss? LOSS, SS function. Now, people point out I did not put an N in there, and it's a little silly of me. But what you have to do is at the right now, because there's only one data point going in at a time, it doesn't matter, but we might in the future. So what we'll do is once in our loss function, once we sum them all up, we say J is equal to 1 divided by, is equal to J divided by the length of your Y data. So that's dividing by N. Okay. To add that in there. Right now, if we're sending in one data point, we're dividing by 1, which mathematicians tell you doesn't make a big difference. Okay. And just as a reminder, these terms are regularization terms. Everything in red here, we're ignoring for today. That's just for later. When we're talking about regularization, because we're not worrying about that for now. Okay. So, all right. There's your loss function. What does it take in? It takes in your Y hat, which is your prediction, and your data. So we haven't defined our data yet. So let's just put in an arbitrary number, let's put in 1. So we need to define data still. Okay. Let's just see if this runs. Does not run. Oh, I'd have to rerun everything. Sorry. Okay, what's going on here? Y hat H list 2, H list 2. All right. All right. Why is yeah. Okay. I see some questions in the chat. All right. What do we got here? Trace back, loss function. All right, and loss function object int has no length. Oh, it's okay. It doesn't know it's a NumPy array. So what we're gonna do, so this is not gonna be a problem for now. We're gonna comment out this line. It's creating a problem because I'm sending in just a variable and not a NumPy array, so it doesn't know what a length is. So later on it'll work. We'll need it, but we won't need it for now. So I'm going to comment it out. Okay. I just commented out this line where we divide by n. All right, that should do it. Let's see if that fixes it. Okay. We got another error. Wait, did I miss something? Where's length? Oh, it's the same deal. Okay, so we don't even need the we don't need the loop either. That's the problem. So we'll just get rid of the loop. And there's no need for. I've made everything so complicated. We're not making this a loop anymore. It's creating too many issues for right now. Yeah. All right. Got rid of all the indexing, all the looping. Now it seems to work. Okay, if you need to look at that, there you go. That's it. I'm going to throw that into the chat so you can all see. Okay. All right. So we got that. So now we are doing forward propagation, theoretically, right? So this is, right now, if we have a certain value of X, this will spit out the value of the the output of the neural network when we set in a value of X. Right now, our X is 0. I think we said up here, yeah, X is equal to 0. If we wanted to plot, let's create a loop. Let's loop the neural net so we can plot. Plot the curve. See what it looks like real quick. All right. So what we can do is we can say for I is in range of some, we want to plot it over a whole bunch of ranges of X values. So we got to make a whole bunch of X values. We'll call them X plot. Actually, don't we already have an X plot? We do. We already have an X plot. X underscore plot is in range of 0, the length of X plot underscore plot. We want to put this all in a loop. There's no, sorry, it's not, what is this, MATLAB? So yeah, then a colon. Okay, so this will loop everything here. Now we just need to say that H list is equal to X plot and whatever the current index I is, right? And then it'll give us an output. So let's have Y hat also be in a loop. So we need to make it a, so we need to make it the same size as our X plot. So let's just create a Y hat plot. Let's make it an NP array. So I'm gonna make it zeros. And we'll make it 1 and 1,000, the same size as our array up above. Okay, np.zeros, and then we'll say Y hat plot is equal to hist2, and this is iter I. Then at the end, we can say, hey, let's plot this. Let's plot what our neural network output looks like over a range of X values. So we would do plt.plot, and we would plot X plot versus Y hat plot. Okay, and then plt.show open close. Boom. Let's see what happens. Do not like that. Okay. Most recent could not return 1,000 as a data type. Oh, okay. I need to include an extra layer of parentheses. Apologies, because I have to send in a tuple. Did not like something. Index out of bounds. 0 in range, 0 range here. Did I have 1,000 or not? Yeah. 0's 1,000. But that's for a vector. Is it 0's 1,000 for? I don't need a matrix of 1,000 zeros. It's just I need to create a 1 by 1,000 array, right? For a vector. Okay, cool. We'll do it that way. Oh, it's right, because I need to make a vector. I made it a matrix. That's why I got confused. Yes, you're absolutely right, Marco. Thank you, Marco. All right. Hey, that's what our neural network looks like, right? Look at that. So here's the question. If we magically knew the right weights and biases to match that curve we did before, will it look just like it? Well, let's find out. I'll tell you, here's what we'll do. We're going to plot the target function that we want, which is plt.plot xplot. And then our target function, let's look, where is it? What was it called? It was just called yplot. Yplot. And let's make it R, and I think double dash will do it. Yep, there we go. Okay. Sure enough, that's the target function that we want. And that's the function that we've got out of our neural net. So if we got the right weights and biases in there, it should match up those curves, right? So let's, for instance, let's go to where we defined our target function. In essence, this innermost multiplier here, that is our weight going into the first layer. And this is the bias. So -1 is the weight, -4 is the bias. And then here's the next weight, which is 2 and 3. So the weight should be -1, 2, and the biases should be -4, 3. -1, 2, -4, 3. So let's change this to -1, 2, for a bias -4, 3. And let's run everything. We run it. Look at that. Perfect match. Okay? So we know for a fact that this neural network can match this curve. So now we got to get it to do backpropagation. Okay? So for backpropagation, we got to follow to the next stage here, which is doing our gradients. Okay? So let's do this in this sort of pseudo looping way. And then next time, we'll probably finish up our backpropagation. And let's see, we got about 10 minutes left. What can we get done in 10 minutes? We can finish up, we can continue on with backpropagation, and we'll try to loop it properly. So that way we're not doing this awkward pasting of code. Let's go back and comment what we've got actually for right now. Okay. Your code, your Y is a straight line. We don't want that. Okay. So we got x hat plot. I'll tell you what, I might be able to share the link here. Can I share real quick? Share. Let me share, copy a link. Anyone with the link can view. If you want to follow along live, we'll put this in the Zoom chat. Okay. Be able to follow along live, I think, as I'm coding. I'm not sure exactly how live it is, but if you refresh, you can definitely see the code I'm putting out there. So let's comment. So this is the activation of layer 1. This is the activation of layer 2. All right. We got that. What's other things? Any other questions, by the way, before we move forward? We are literally following this formula, and sure enough, it's created a function we know it can create. We can even sort of fudge the weights and biases around. Like if we change this weight to like 2.1 and reran it, it should be slightly off, right? 2.1. There we go. See, look, slightly, oh, more than slightly off, actually. Okay. Right. Back to 2. It's a perfect. Okay. All right. Let's run everything. So let's do some initial backpropagation. So let's do some backpropagation. Okay. So for backpropagation, here is this formula here. First thing we need to be able to do is take the gradient of our loss function right here. Go back here. We have to take the gradient of our loss function, which is frankly quite simple. We did it yet last time. It's going to be 2 times our prediction minus y, right? So we have to be able to put in some data point right now, okay, for the actual data. That's pretty simple, right? In fact, let's put it in a gradient, its own function here. Let's go back to the code. I'm just going to make a new function right here. I'm going to define, I'm going to call it the loss underscore gradient. What does it need? It needs our y prediction, which I believe comes out of, yeah, we'll call it y hat, and compare it to some y data. And what does it return? It returns 2 times y hat minus y. Okay. Oh, that was hard. Look how long that is, right? This is our, in case we need to comment on it, it's just the gradient of our loss. Backpropagation. So now, the first step, this right here, is the gradient of our loss. And so we would say that G is equal to our loss gradient, okay, times which of our y hat, which is our prediction. Okay, so we would need to get that from our previous loop. Right now, we just have it for a whole bunch of points, but we'll get that from the forward propagation, right? And our y for our data. Okay, we have not defined those yet. I'm fully aware. Okay, we'll have to add those in later. In fact, for right now, let's just say, you know, this is a temporary, just so we don't get an error when we try to run it. Let's just say that y hat equals 1, and that y data is equal to 1. This is also temporary, just so we don't get errors and warnings here, okay? So this is that first step here, right? See that? All right. Now we have a loop, and we're going to kind of fake the loop here, okay? And then we're going to say, hey, our gradient, we're going to update it by taking that gradient and then multiplying it. That's the Hadamard product. It's more for vectors, but right now we're not dealing with vectors. So just a multiplication of f prime, which is the derivative of our activation function, of a of k. Keep in mind, these a of k's we stored up above in our code, right? So if we're starting at the largest value, L, right up here, L is 2, right? It's going to be A2. And look, A2. We have it stored. Awesome. A2. Now, so that means this code, so that means G is going to be equal to G times F prime. That's the derivative of our activation function. Well, that's something we can define in a function. So let's do that up here. Let's go here. So this is going to be the derivative of our activation function. This is the only derivative we should have to take for the rest of this entire experience of doing backpropagation. You're not taking giant derivatives, you're taking little derivatives, and only have to write it out one time. The derivative, we can call it activation derivative. It takes in just some input, we'll call it x, all right, and we need a semicolon, right? And all it does is it returns the derivative of our activation function. Friends, what is our activation function? It's that hyperbolic tangent. It's the only derivative you'd ever have to take. You can look it up. The derivative of the activation function, which is the hyperbolic tangent, you can look it up. It's the secant. It's the hyperbolic secant squared. Okay, you can derive that on your own time. And then you say mp.sech. This is all within NumPy, so we can take the secant and of x, and then we square it. Done. Okay. Okay. You can look it up. It's in a table. The derivative of a normal tangent is secant squared. Same with the hyperbolic tangent. Okay. It's hyperbolic secant squared. All right. G. Now we have the activation derivative. We have that function. We can, and also per my naming convention, I want to make it a capital A. Activation derivative. And it takes in, as we mentioned, AK. And if we're starting K at the value of L, it's A2. A underscore 2. Okay. Awesome. Now, next step, we need to say that we want to store our gradient of our bias K. So we'll call that grad bias K, which will be 2, okay? It's just equal to G. And again, all this other stuff, that's for regularization for later. Okay, next step. The gradient of our weights. We'll call this grad B for the gradient of our biases. Next one, we'll call it grad W2 is equal to your gradient times HK minus 1 transpose. We're not dealing with vectors right now, so we're going to ignore the transpose for the moment. So it is G times H underscore 2. Is that what I called it? H list 2? I call it H list 2 because that was a very silly thing for me to do. I'll call H list 2, right? This is our gradient of our weights. Okay, we are almost done. Literally, we have like 2 more lines of code to write. Okay, something like that. Now we have to say that G, this right here, G is equal to your weights from that layer, which I would call, which is W list, and it is the second layer, and it's the second index, which is 1 in Python times G. Okay, that back propagates from layer 2 back to layer 1. Now we want to back propagate to the beginning. We can do this really quickly. We can say that all these steps, we are looping them and going back to here and just changing the index, right, down to 1. So we're going to do this very sloppily. I apologize. Just to finish, I'm copying all these, and I'm changing this A2 to A1. I'm changing this grad 2 to B1, this grad W to be grad W1. This is H list 1, and this is W list 0, and we're done. That's back propagation. Just following the formula, a little bit sloppy. We'll make it a little cleaner next time. Okay, it's H list 1 due to H list minus 1. Yes. Yes. Thank you. That's a good catch. This should be H list 1. And this should be H list 0. Good catch. Because we have H list 0, right? Yes. Does the H show up anywhere else? That's good catch. This should be H list 1 and 0 because, as they pointed out, this is a K minus 1. Hopefully this will be a little bit clearer when we do the loop itself. But that's the process. Any questions? Then I guess we can run it to see if it actually, yeah, I guess we have an error. Let's see, can we fix any errors? I didn't have to run everything. All right, I have an error. Secant H. Did I not get the hyperbolic secant right? Excuse me, let me look up the hyperbolic secant real quick. I thought I had it off the top of my head. There. NumPy, hyperbolic secant. Huh. SciPy. Let's fix the secant. Yeah, there's no secant H. So, okay. So let's just actually do the actual formula for secant. That's lame. Thank you. Let's fix the secant. So instead of it being, we're just going to the derivative of the activation function. We're going to do a secant is just 1 over the hyperbolic cosine, right? So it's be 1 divided by np dot cosine h of x. Change that out. Now let's run it all. I don't believe that gave us an error. Great. No errors. Okay. I think we'll stop there for today. Happy to stick around for questions. I appreciate that, folks.